In this video, we'll be discussing logarithmic functions as inverses and how to write and evaluate their expressions. So logarithms versus exponentials. A logarithmic function is actually the inverse of an exponential. So in a previous video, we discussed about what like exponential growth looks like. So if you had y, we talked about y equals a times b to the x, and what that looks like. For example, y equals 10 to the x is an exponential function because you have a variable that is in the exponent. A log function or a logarithmic function is actually the inverse. So if you were to draw the line y equals x and you were to fold a piece of paper over it, an exponential function would actually overlap onto, which would become a log function. They are actually inverses of each other. So a logarithm to the base b of a positive number y is defined as the following. If you have y equals b to the x, which is an exponential function, then you could write the inverse as log base b of y equals x. So the variable or the base becomes the little base of the log. The exponent is what it gets equal to, and then whatever it equaled becomes part of the log. I know that sounds kind of weird, but for example, if 5 squared equals 25, that means log base 5 of 25 equals 2. And again, you could think about it as in like this little number raised to the 2, that number raised to the 2 is going to equal that number, which it does. 5 squared does equal 25. Same thing with 7 to the third. So the base of an exponential becomes the base of the log. The exponent becomes what it's equal to. Same thing here. The base, which is 8, becomes the base of the log. The exponent, -2, is what it becomes equal to. And then 1/16 becomes the other part of the log. There's something called a common log. A common log is a use of base 10. So for example, y equals 10 to the x and y equals a log of x are inverses of each other. If there is no number as a base of the log, it is automatically assumed to be a 10. Now you can actually find the logs of these by pulling up the calculator. So for example, log 10, if you hit the log button and then log 100 and hit enter, you will actually get a 2. Log of 47, so you hit log 47. You don't have to close the parentheses here. You will at other times, so it's a good habit to have. It would be 1.67. And then log of a -35 is actually going to be a non-real answer. So you actually cannot have the log of a negative number. And again, if you look back in terms of the log, you cannot have a negative number. Negative numbers are over on the left-hand side of the the x-axis. You cannot put a negative number into a log. It is only positive numbers that are allowed. So you can actually find the answers to these. So we found that the answer to this is 2, and the reason is because this log basically has an understood 10. And 10 squared does give you 100. So this little 10 raised to the 2 actually does give you 100. Log 47, I believe we saw was like 1 point something. Was 1.67. So this 10 to the 1.67 does give you the number 47. And of course, we learned that this does not exist. You cannot do it. You could say that there's no solution or it does not exist. There are other log properties to know. So if you have a log base a of 1 equals 0, log base a of 1 is going to equal 0 because any number raised to the 0 power gives you the number 1. Any log that has a base of the exact same number is going to equal 1. For example, like if I had log of base 3 of 3, that is going to give me 1 because 3 to what power gives me 3? The answer is 1. Same thing here. If I had log base 5 of 1, that is going to give me 0 because 5 to the 0 power is the number 1. Same thing here. 3 to the first power is the same thing as 3. If I had log of base 5 of 5 raised to the x, we know that log base 5 of 5 cancels each other, leaving you just the variable x. Same thing here. If I had log base 5 of x and that equal to log base 5 of y, that means x and y both must be equal to each other. So you actually can evaluate logs even with different bases, and it is called the change of base formula. So for example, if you had log base 4 of 27, then in your calculator, you're going to type log of 27 divided by log of 4. So if you pull the calculator back up, let's move it closer. So what you would do here is you would hit log of 27. Here you have to close the parentheses because you will get a different answer if you don't. And then, that's not it, sorry. You would get, you would get log of 27. Make sure you close the parentheses here, divided by log of 4. If you do not close the first set of parentheses, you will get something different than the correct answer. So be very careful. And you will get 2.38. So this would represent 2.38. In this case, log of 42, since it's already an understood 10, then you could just say log of 42 and then hit enter. You would get 1.62. But just to prove that it works, log of 42 divided by log of 10 gives you the exact same number, 1.62. Log base 5 of 10, in your calculator, you would type in log of 10 divided by log of 5. Just make sure you close the parentheses. Same thing here. You would do log of parentheses 1 divided by 12 divided by log of 4. So you can actually put all these into the calculator in order to find your answer. Now, a real-world connection, the pH level of a substance actually equals this formula. So you have the pH of a substance equals negative log base 10, because there is no number down there, of the concentration of hydrogen ions. So they want to know what is the concentration of hydrogen ions if the pH level is 2.3. So you're going to substitute 2.3 in for the pH, and you are going to find out, in order to rewrite this, I first need to get rid of my negative. So I'm going to divide both sides by a -1. So I know that negative 2.3 is going to give me log of my hydrogen ions. Now this log has a base of 10 that is understood. So you can rewrite this as an exponential. This base raised to the exponent, so 10 raised to the negative 2.3 is going to give me the number or concentration of hydrogen ions. And so if you type that into the calculator of 10 raised to the negative 2.3, you're going to get 0.005. That is the amount of concentration, the concentration of hydrogen ions in lemon juice. Again, the first thing you have to do is get rid of the negative, and then you rewrite the log as an exponential. The log has a base of 10, so you can rewrite it as this base raised to that becomes the exponent is going to equal this inside. So to recap, let's write this in log form, and then we're going to write this in exponential form to work back and forth. So I want you to attempt these problems, so pause the video and then resume when you're ready to see the answers. In this first one, log form, it is going to be log. This base becomes the base. So 4 raised to the 3, so 4 raised to the 3 is going to equal 64, which gets placed there. And so this is how you would write it as a log. again, the base of the exponent becomes the base of the log. The exponent becomes what it's equal to, and then the 64 goes there. In this case, you would write 3 raised to the 0 is going to equal the number 1. So if you have it in a log form, you can rewrite it as an exponential, and if you have the exponential form, you can rewrite it as a log.